So in this video, we're going to talk about the laser 3dB frequency. And the 3dB frequency is just a standard way of quantifying the speed of something. So it's the frequency at which, so this sine wave at which, when we feed in a sine wave, we get a sine wave with half of the output power, or 1 over root 2 of the amplitude. And it's a beautifully standard metric for quantifying speed. So in the last video, we saw that the dynamics part of the laser transfer function, so ignoring the, say, the P naught, the DC power term out here, all the interesting stuff, or at least the stuff we're interested in right now, can just be written as a standard second order system. So I'm just going to write this in the standard normalized form. So in terms of zeta and omega naught, so minus omega squared over omega naught. And this is our normalized transfer function as a function of omega. And you can calculate the 3dB frequency for this. So you can just plug this into your favorite computer algebra system. And to simplify things, we're going to assume that zeta is much less than 1, or we've got a small amount of damping in our system. And initially that's going to be valid for small omega naught, but we'll revisit that later. Then you can calculate the 3dB frequency. It's just your system's resonant frequency times the square root of 1 plus root 2, or approximately omega naught times 1.55. And so at least for small zeta, the maximum speed we can operate our laser at is just linearly dependent on the resonant frequency. So we want to try and maximize this. And we said we solved for the resonant frequency in the previous videos. This was just equal to, I'm going to write it as two separate terms. So the group velocity times our differential gain G prime times gamma. And these we can think of as material parameters. So we're almost always going to want to increase gamma as much as possible, and G prime and Vg. But once we choose our material and the material system we're using, there's really not much we can do about these parameters. So they're not terribly interesting in terms of maximizing our speed. Now the other thing, so the other term of omega naught, so this just needs to be multiplied by the number of photons in the cavity, or the DC number of photons, divided by the photon lifetime times the active region volume. And so there's a few things we can do now to increase our resonant frequency, to increase our laser speed. The first is we can decrease the photon lifetime. So this will increase our our resonant frequency. And this sort of makes sense, right? Because as our photon lifetime goes down, this just means that the photons in the cavity can build up very quickly and dissipate very quickly. Build up very quickly, dissipate very quickly. So decreasing the photon lifetime actually will improve our speed. And you can do this primarily by decreasing the mirror reflectivity, or the mirror reflectivity's R. So remember, the photon lifetime is just how long a photon stays inside this cavity, which depends on the mirror reflectivities. So the more reflective the mirrors are, the fewer photons we lose per unit time. So the fewer photons manage to escape, and the longer our photon lifetime is. So if we decrease these two mirrors, and so I'm assuming that this is our cavity with some active region volume, if we decrease the reflectivity, then we can increase our frequency by decreasing the photon lifetime. But this has the problem of being, this makes our mirror structure, or our cavity, more lossy, which means we need a higher gain to compensate. And so we might need to choose a different material if this is the strategy we want to use. Now the second thing we can do is we can decrease our active region volume. And I also should note that the photon lifetime was also related to the length of the cavity. So decreasing the active region volume also sort of changes your photon lifetime. But we're gonna just treat them separately. And this is fairly simple. If I've got a big device, So if I've got some giant square of active region volume, all I need to do is make it smaller for a given number of photons within the cavity. And that's fairly easy to do. You're going to be constrained by things like lithography. And you're also going to be constrained by, can this structure still handle the current that you're going to inject into it? So you're also going to be constrained by things like heating. But this decreasing the active region volume is a major reason why so many lasers use quantum wells instead of bulk active regions. And we'll be dealing with these later in this series of videos. Now the third thing we can do, and this is generally the most common because it's practically speaking, the easiest, is we can increase our DC photon density, or increase our DC number of photons. And how do we do that? Well, we know that the number of photons, we said in a previous video, for lasers well above threshold, this is just proportional to the current, or if we're being precise, the current minus the threshold current. And so you can think of this term on the left is just the number of electrons injected per unit time. And then we multiply this by the photon lifetime, which isn't super important here because we've already gone over how that affects things. But so here is our interesting, right here, by increasing the drive current, we can increase our DC number of photons. And this is a very common strategy to increase your laser speed. So if you increase the current, you're going to be able to increase your resonant frequency. Or I guess we should call this the DC current I naught. And this in turn will increase your 3 dB frequency and give you a faster laser. So there's three major ways that we've seen just now to change our, to increase the speed at which our laser operates. One is by playing with the mirrors. The other is by playing with the geometry of our device and how big it is. And the third is by increasing the DC number of photons, which we can do by increasing the current. Now another thing we could do is we could decrease this threshold current because this will just increase the number of photons inside our cavity. So that's another strategy that you can pursue. But if your drive current, if your DC drive current is much greater than the threshold current, this isn't going to give you a whole lot of benefit. Now, the next question you might have is, what's the maximum frequency? What's the maximum 3 dB frequency we could possibly achieve with our laser? And for that, we need to go back to our original transfer function. Oh, it looks like I missed a squared there. My apologies. So let's get rid of our initial assumption. So let's say zeta isn't much smaller than 1. So zeta might actually become pretty appreciable. And let's say that omega naught is extremely large. So we've done everything we can to push omega naught higher and higher and higher, and now we just can't do it anymore. And in that case, we're going to neglect, so as we increase omega naught, this term involves an omega naught squared in the denominator. This guy only involves a single omega naught, so we're going to neglect this guy here. So our transfer function, h of omega, or a normalized transfer function, then just becomes 1 over 1 plus j omega 2 zeta over omega naught. And in the previous video, we said we could write zeta, or we know zeta, we just calculated it when we did the laser's frequency response. This is just equal to omega naught tau p plus 1 over omega naught tau n. And so tau p again is the photon lifetime, tau n is our carrier lifetime. And if we again assume that omega naught is very, very large, or is much greater than, say, this time constant tau n, we can neglect this term here. So this term is going to be negligible. So this term grows with omega naught on the left-hand side. This term decreases with omega naught. If we've got a very large omega naught, it's very likely we'll be able to get rid of this term. So fine, let's plug this back into this equation. And so we've got our normalized transfer function, and this is absolutely beautiful. So when you plug in this value for zeta, you'll get that the transfer function is just 1 over 1 plus j omega times tau p. And so from this, we can very quickly calculate our minus 3 dB frequency. This is just going to be root 2 over our photon lifetime. Or if you want it in terms of frequency, instead of angular frequency, it's just root 2 over 2 pi times 1 over the photon lifetime. But they're saying the same exact thing. And so this is really interesting. This says that we're fundamentally limited by our photon lifetime tau p. So once we design our mirrors, once we choose our material, once we choose the length of our cavity, we have our photon lifetime, and we cannot go faster than that. We cannot modulate the light coming out of our laser faster than this frequency. And so that's really good to know, because it means once we engineer tau p, once we choose tau p, no matter how high we pump the current, and no matter what else we do, we cannot do better than this. So I hope you enjoyed the video. If you did, please give it a like down below and subscribe to my channel. Also, if you have any questions or comments, please feel free to post those down below, and I'll try to get back to you as soon as I can. And thanks for watching. I'll see you next time.